to this overcurrent relay is actually 25 amps. All right, so now let's look for what is the positions of this fault current value in terms of plug setting multiplier. So 25 divided with 5, so you can see it's at the positions of 5 taps. All right, so which means that at x-axis here, you refer the values of 5. But if you go back to these figures, right, the time down setting is not being given. So which means that for this relay, you have to decide, all right, what would be the time multiplier setting. So obviously it should be higher as comparing to this relay. Why? Because its operation time should delay. So in this case, what if we choose the time down setting here at 2 seconds, right, which is higher as comparing to the previous relay. So now look for the intersections at y-axis here. So you'll notice that for this relay, in the event if we have 1000 ampere occurs here as a fault, you will actually wait for this time 0.7 seconds. Only it will start to trip the networks as a backup. All right, so now we want to see if the chosen time down setting here correct or not at 2 seconds here. So, and the question has also mentioned, right, the time margin has to be kept at 0.4 seconds. So which means that I need to wait this relay to work first as a primary protections. Wait for 0.4 seconds first. If it's not working, then only I start to take action. So let's see. So for the time taken by the first relay here is at 0.3. The second relay is at 0.7. So if you find the time difference right now, you can see the time margin is actually fulfilled at 0.4 seconds. So this indicates that if you select the TDS, the time multiplier setting here for the second relay at 2 seconds, this is actually correct. So that's how we solve this examples here. So do you have any questions? Hello? 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 Chong have no questions. Okay, so if you have no question, I will give you 5 minutes break first. Then we will proceed the next topics on different kinds of overcurrent relay. So please come back at 4:11 p.m. Okay, so uh, 5 minutes have passed. So let's proceed to the remaining topics. Just now we have gone through the general working description for the fields, the overcurrents relay, and in order to have the time coordinations for backup protections, let's say we have overcurrent situations, we know that fields is not suitable, right? That's why we use overcurrent relay. And there are two settings we can adjust for an overcurrent relay. There are the plug settings as well as the time multiplier setting. And we have gone through, if not mistaken, we have two examples here to understand how we can do the setting for the relay. Let's say if we are using more than one relay for overcurrent protections. So this time we'll go into these topics here where we have four different types of overcurrent relay we can use. So we'll understand the characteristic of each types of overcurrent relay in terms of how it's dealing with overcurrent situations. So let's move on to the next slide here. So whenever we want to decide in terms of settings for the overcurrent relays, right? Let's say we have more than one relay being used to pick up the overcurrent situations. There are two important requirements should be considered for a protective relay. The first one is selectivity. The second one would be in terms of speed. So the fundamentals behind these two are actually the coordinations between the primary and backup protections. So if we talk about in terms of selectivities, so for this relay, which is worked as the backup, right, will only operate for those fault that occurs only within its zones here, which means that if let's say if the primary protections fail, only backup protection will start to work. So for backup protection is being intentionally set with lower speed in terms of fault eliminations. So if we talk about primary protections in terms of speeds, of course, it should be fast to clear the fault in the event if the fault occurs within its zones. So that's how we base on these two requirements here to do the setting for the overcurrent relay. So for good selectivities, as or I should say the good discriminations for the faults for overcurrent protections can be achieved by using this three way. First is via current discriminations. So current discrimination, which means that based on current value, so in terms of pickup current setting. All right. The next one will be in terms of time discriminations, in terms of relay operations time. So if there's a need of coordinations, we will need to have this time discriminations or the combinations of these two, which is current time discriminations. So because of this three way, it gives us four different kinds of overcurrent relay. Okay, there are the deference current relay work based on the pickup current value. Deference times rate work based on the time you have set. Inverse times rate so based on inverse time characteristic. Later we'll see how it works and the combinations of these two. All right, deference time difference times and difference current and inverse times relay. So it forms us the last one. All right, so now let's see how does the difference currents relays works. So let's move to the next slide here, which is the most basic types of overcurrent relay we have. This different current relay also can be called as instantaneous relays. So the ideas behind this relay is like this. Whenever the currents reach its specific values, which is the pickup current value, usually will set near to the fault current value, which is slightly lower. So under these situations, this relay will work instantaneously, which is exactly at the instant when the fault occurs without time delay. So let's check out this graph here. So we have time current characteristic curve for this difference current relay. So let's see how it works. So we have y-axis here being plots with the relay operations time. S-axis here is the current flowing through the networks. So what happens if the current flowing through the networks right now is increasing, right? But below the pickup current value? Under these situations, we are having the healthy conditions. So no response from the relay. All right, so there will be no tripping occur. So what happens if the current is reaching the pickup current value, which is the setting current value for this relay? So now you can see at time t at 0, right? This relay directly send the tripping impulse to the circuit breaker. So it will start to break the circuit. So you can see, and after this pickup current value, here is actually the tripping areas of this damage current rate, in which at time t at 0 during the fault occurrence, whenever it's detected, it directly trips the networks. So you can see this relay doesn't wait for any time to trip the circuit. All right, that is what we have as a deferred current relay. So for these kinds of relays, right, is very suitable, especially for those systems that are expected to have large fault current value. Why? Because if we have large fault current, remember it will create a great damage. So we doesn't want to have this high fault current stay in the system for long durations of time. So we need the instant break. That's why we'll make use of definite current relay. So with the fact that just now we have studied wherever we have fault occurs furthest away from the generation source, the magnitude of the fault currents will be much more lower, seeing as the impedance is highest as the furthest point. Do you still remember this? So with such a case, if I'm using more than one deferred current relay within the power networks, right, the setting has been chosen in this way, whereby for the relay that locate at the substations, which is furthest away from the generation source, it will pick up at much lower current value. But if I have the relay that is moving closer to the generation source, you will notice that the pickup current or the operating current value is increasing. All right, so to further explain this point, let's check out this diagram here for better understanding. So now I have the reduced power networks. I have a generation source after the transformer is feeding this line. And the line has been divided into 3 sections where substation A, B, C, and D here. And then each section has been implemented with the relay R1, R2, R3. And this relay is getting the current measurement from this current transformer. Okay, so now we are, let's say this R1, R2, R3 here, we are using different current relay. So the horizontal axis, from looking from the generation source here, we know that this is the distance of the relay as comparing to the generation source. And the y-axis here is actually the pickup current value expressed in the units of per unit. All right. So now you can see that for this substations D here, where we have a relays located here, furthest away from the generation source, in terms of pickup current value, it will be the lowest. So if we're getting closer to the generation source, for example, this relay 2 here, the pickup current value is getting higher and higher for relay 1. So that's how we can do the setting. So with such arrangements, the relay with lower setting will start to operate first and disconnect the load whenever there's a fault occurs near it, right? So that's how we do the setting for the deferred current relay. So now we know that for the instance break is actually advantageous of this first kinds of relays we have, right? But at the same time, it gives us problems whenever we have the instantaneous break without any times delay. All right, so now let's see this diagram here. What if we have these situations? All right, we have a generation source feeding these two lines. Let's say it's being split into two, and this two line is very short. All right, so what happens if we have fault occurs in between like this? And we are implementing the deferred current relay for these two short line. So n equals of 50 indicate this is the overcurrent relay. Okay, so now these two short line will have low impedance value. Are you agree? So which means that there will large fault currents being flowing through these two relay right now in the event if there's fault occurs between these two short line. So what happens if you have high magnitudes of fault current flowing through these currents relays here? So which means that these two relays will work at the same time. So it will trip the circuit. So it doesn't allow to have the backup protection in such a case. So there's no coordinations between them if we have this deficit current relay is being used. And then we have another problems as well. What happens if we are applying a weak generation source? So for example, we have a generation source feeding this line. If we are using a weak generation source, which means that the impedance imposed by this generation source is low, what happens is impedance is even lower as comparing to the line right now. So with such a case, yes, we are using deficit current relay for these two sessions here. So in the event if we have fault occurs here at the ends of the line or occurs here near the generation source, the fault current's magnitude is actually very close as comparing to each other. Why? Because here the impedance is low. Alright, whenever it's low, the magnitudes of the fault current generated is actually looks alike or having the same magnitudes as the one that occurs at the ends of the transmission line. So with such a case, these relay can't tell the difference whether this fault is occurs here or here. All right. So this is only occurs if the generation source is very weak and causing its impedance value is actually bigger as comparing to the transmission line. That is the another problems we have. We have few small scenario that causing this deficit current unable to work properly. So which means that it's unable to tell the difference where it occurs. Right. So now let's check out these examples here. So what happens again, generation source of the transformer feeding this line that's been divided into two. And we have been implemented these two zones here with the deficit current relay. So what happens if we have this fault occurrence? So let's say this is long line, this is short line right now. Of course, short line, the impedance is lower as comparing to long line. So if you have such faults occurrence, F1 is occur down the long line, F2 is down the short line. So with these situations, right, the magnitude is actually quite same and it could be causing the magnitudes of this occurs, of the fault currents that occurs at the long line here, even lower as comparing to the short line. So under these conditions, the relay can't tell the difference, right? Where does the fault occurs? And then we have another situation, all right? What if we have a generation source used together with the transformers right now, okay? And this transformer will build up the overall impedance at the source side. So what happens if I have these two fault occurrence? F4 is occurring at the source here, which we have a source connect with the transformer. F3 is actually occurs at the beginnings of the transmission line. So seeing as this transformer build up the overall impedance, it might actually cause the fault currents occurs here much lower as compared to the fault that occurs at the beginnings of the line. If let's say these two faults are physically close together. So under this situation, again, we have the second scenario here where this relay unable to work properly for overcurrent protections. Okay, talking about more in terms of limitation for different currents relay. All right, so let's say we want to do the settings. So if we have different current relay being set in this way, which work based on the maximum fault currents level. So under these situations, right, it might be not suitable if, let's say, the fault current value is much more lower. So which means that we have SKB fault. Or if you set in reverse conditions, what if I set it to be picked up at much lower fault current value instead? So if much lower setting, which means that we might have unnecessary tripping if, let's say, the fault magnitudes have already increased. So in such a case, you can see to do the setting is also very hard as well. So for this deficit current relay. And you can also see that you can't use it as a sole overcurrent relay for overcurrent protections, right? Instead, based on its advantages here, seeing as it's able to trip as an instant whenever there's a fault occurs, we will have this deficit current relay here work as Instead, you need together with another kinds of protection. For example, use together with the distance relay or the differentials relay so that you can have it to operate much more faster. Alright, so due to these limitations, we have another kind of relay is being created. So it's known as default times relay here. So for this relay, right, there is a time delay for it to wait before it start to trip the networks. So with such a case, it can cope with much more different fault currents value by using different operations time. So let's check out this working operations curve for the default times relay. Again, we have y-axis is the relay operations time. S-axis here is the current flowing through the networks. So what happens if you increase the current flowing through the networks? So before a peak current rate, of course, there's no tripping occurs because this is a normal situation. So what if the current flowing through the networks is reaching the pickup current value? So you see, right, this relay will wait for some time, which is the delays of time that has been being implemented. So once this delays of time has been expired, then only it will start to send the tripping commands to the breakers. So you can see these blue areas here is actually the tripping areas for the default times relay. So you can see we have two settings round. One is the relay operations time. Another one is a pickup current setting. But for definite currents relay, right, we only have pickup current setting. Only left and right, no up and down. But for different times relay, you have two settings instead. You can actually delay its operations. All right, so let's continue to the next slide. Okay, so now how actually we can adjust the time setting for this relay so that we have a coordination for both primary and backup protections. So it's actually doing in this way. So apparently we can have more than one overcurrent relay is being used for systems. So let's say we have a generation source of the transformer. Again, we have a line divided into three sections where bus bar A, B, C, D here. Each sections were implements with different time relay. Okay. So again, the x-axis is showing you where does the relay locate, referring to a generation source. Y-axis right now is telling you in terms of operations time for the relay. So the setting has been done in this way, whereby we has been adjusted in a way where the breaker which is nearer to the fault to trip first with the shortest time, and the remaining breakers in the successive zones will use much longer time whenever we are moving towards to the generation source. So if you follow this point, this will telling you that R3 will have the fastest operations time. Okay, whenever we move closer to the generation source, like relay 1 here, will have a longest delays of times. All right, so now to further see these figures, right? Remember, I have tell you the vertical axis is actually relay operations time. So now let's say I have fault occurs here between line sections C and D. All right, at this particular fault current value. Fault occurs here. So we know that this is time t at 0. For this relay tree, right, it will directly trip the fault, seeing as it occurs as the internal fault. Right? And we know that relay 2 should work as a backup for relay 3. So for the fault occurs here. So you can see, right, we have a discrimination margin TD here, which is the time margin, where this relay 2 should wait for relay 3 to work first, then only it start to trip the fault occurs within C and D. So you can see the time is not operates here, but here instead, which is already delayed by this time margin. So how about for relay 1 here? What if relay 2 also doesn't work? We will have relay 3 work as backup for this relay. Sorry, I have relay 1 work as backup for relay 3 here. In the event if I have fault occurs here. So this relay 1 will wait for another time margin. Let's say here is 4 seconds. Here is another 4 seconds. So in the event if I have fault occurs here between C and D, this relay 1 will wait for 0.8 seconds first. All right, to have this relay 3 and relay 2 to work to trip first. So that's how I do the setting. So for the relay that is getting closer to the generation source in terms of operations time is actually much more longer. Okay, the one that is furthest away for a generation source, in this case like R3 here, there's no delays of time is being designed. All right, it will strip the fault at the instance whenever the fault occurred. So relay 1 wait for the longest time. Relay 3 doesn't need to wait before it start to issue the tripping command. Okay, so now why we need to have the delays of time, or I should say why I want to use such kinds of relays in a power system. So the protection from no fault conditions like the motor startup currents as well as the transfer inrush current as well as the transient fault. So remember what I've been mentioned just now based on the applications. Let's say I'm using the deference times relay to protect the motor here from overload conditions. So during the motor startup times, always the current drawn from the motor source is much more higher, right? That is the normal situation for the motor. So we need the delays of time for us to go through these normal conditions of the motor during its startup time. That's why we use step times relay, all right? Or for the transformer, for it to compensate the residual flux within the core. So this inrush current is higher than the normal current conditions, and this inrush current is not considered as a fault, and it will not stay high always. So we need to have the delays of time, stop the relay from operating, and allow this transformer to start up successfully with its inrush current go back to its rated current value. So with the delays times relay being used, it allows us to go through the non-true fault conditions. And at the same time, we could have transient fault as well, but it doesn't need to be being tripped. So these delays of time also allow us to go through as well, right? So that is the functions of definite times relay. But at the same time, right, this deficit time should also help to solve the problems that we have seen for the first kinds of relays we have, which is a deficit kind rate. Remember, so what we have these situations, okay? So what happens if I have weak generation source, all right? And then the weak generation source here causing the impedance is much more higher as comparing to the transmissions line. And if let's say I have fault occurs here or occur near the generation source, basically if I using the deferred current rate, it can't tell the difference whether it occurs at the beginning or at the ends of the transmissions line. So in such a case, I can make use of delays of times right now for this relays. All right, so for example, if I have fault occurs at the end here, I should have these relays to work first. So I will have the delays of time, which is much more faster. So you set it at 0.1 seconds. And then I should have this relay here should not work for this fault, right? Okay, so I will have this with much higher delays of time, which is at 0.5 seconds. So which means that if I have fault occurs at the ends of the line, so if let's say this relay is already worked to trip it at 0.1 seconds, so we will not have this relay work to trip this fault. So that's how we solve the deficit currents relay. Okay, but it has problems. Remember, we might have fault occurs at the generation source, right? If let's say we have this relay work with much more slower response, right? So this indicates that in the event if I have fault occurs at the generation source, this fault current will stay for longer durations of time, which is at 0.5 seconds. So this fault current might be damage the generators right now, seeing as generator is very expensive components. So this basically showing you the problems of using the definite time relay in which the time greatest rates right now where the heaviest faults, which is expected to have much higher fault currents rate, will spread the slowest, right? We should have smaller delay in terms of time to clear this fault, especially for these sensitive elements here like the generators, okay? Because of these limitations, that's why we have third types of overcurrent relay is being introduced. So we have inverse times relay instead. So as its name you can tell, right, its operation is actually inversely. So this relay will work in terms of time inversely proportional to the fault current following this relationship here. So if your fault current is high, the operation time is low. Okay, if your fault current is low, the tripping time taken, which means that delay is actually much more higher. So this is basically the inverse time relay where it solves the problems of the difference time relay. So which means that the higher currents right now will trip the faster without the risk of protection selectivity. So let's see this curve here, the time current operating characteristic curve for the inverse times relay. So y-axis again is the tripping time, x-axis is showing the current flowing through the networks. So what happens if I have small fault currents value or I have small pickup currents value? So check out this orange line here. So you'll notice that if you have this amount of delays of time, okay, what if I have much higher fault currents value, right, with this pickup currents value? Check out the red colors line here. So whenever we have high fault currents value, so it will have shorter, smaller amount of delays of time. So that's how we solve these problems. Okay, whenever the fault currents here is high, so if we are using the inverse times relays, right? So it will have smaller in terms of delays of times. Okay, so now let's see next slide here. This inverse time rate allows us to have faster in terms of killing the fault for those fault that occurs near the relaying point as comparing to the difference times relay here, while it's maintaining the same selectivity as well as backup protections. So how actually I can draw these conclusions here. So let's check out this image here to have a better understanding. Okay, so the networks here is the same generator, transformer, the line divided into three sections where substation A, B, C, D. Each sections here I have implements with the overcurrent relay R1, R2, R3, and this is the symbols for the current transfer where how this overcurrent relay takes the current measurement. Now I'm using different kinds of relays for this R1, R2, R3. So now you can see the line current, right? I should say the line here with the labels of 1 is the characteristic curve for the difference times relay. So you can see based on the time you set, this is actually is operations curve. And then at the same time, I also can use the inverse times relay, and this is its operating curve. All right. So now if we comparing these two, this is difference times relay. This is the inverse times relay. So now, in the event if I have fault occurs here in between A and B, let's say here, okay? So you can see, right, in terms of operations time, for inverse times relay is actually much more faster as comparing to the difference times relay, okay? That is how we maintain the selectivity with faster clearing of time for the fault occurs. And at the same time, we could have backup protections. So you will see its curve, right? For this relay, this is its curve, all right? From say substation A up to C here. So you can see from B to C, these sections where relay will work as a backup for relay 2. And this is the curve if I'm using inverse time relay. So here you can see it work as a backup for relay 2. So you might confuse, how about this one? This is the curve for relay 2. This is the curve for relay 3 if all of them I'm using different times relay. This is the curve for R1. This is the curve for R2. Here is the inverse time characteristic curve for R3. Okay, so now what happens if I fault occurs here between B and C? Okay, you can see, right? Either you use difference times relay or inverse times relay, right? Here, there is a time discrimination, which is a time margin, or here, this is time. Let's say we talk about the inverse times relay first. In the event if I have fault occurs here between B and C, I know relay 2 should work as a primary protection. So you check out the operations time is much more faster as comparing to this curve, in which here is from R1 will work as the backup. Are you able to see? What if I change to Devil's times relay? Okay, if I have fault occurs here, this is from R2. R2 will work to trip the fault. R1 work as a backup for R2. It will wait for this time delay, only trip here as a backup. So you can see, right, regardless you're using the first times relay or the inverse times relay, we could also have the backup protections. But for the inverse times relay, it could have fastest response as comparing to the first times relay. That's how we draw these conclusions. And then moving on here, the inbuilt ECA unit attached to inverse time relay can further reduce the tripping time for the fault occurs near the relaying point here. All right, so other than this, right, you can also notice that we know this is an inverse time relay, right? Labels with numbers 2. And these operations times of inverse time relay can further improve as well, which means that we want it to operate much more faster, which reduce TMS. All right, so what if I reduce its time multiplier setting here? I have the inverse time rate labeled as this red color dotted line. So its operations time is even faster as compared to blue line, right? So you can see this inverse time relay, its operations time can be has make it faster as well if we reduce its TMS value. And then we have another kinds of relay in which we will discuss later in as the four types of relay, where we'll have deference time relay attached together with the inverse times relay. So giving us the four types relays right now. So whenever we use the combinations of the features of these tools relay, basically we're able to reduce the tripping time even further. So for example here, so we know the dotted line here is the inverse relay with reduced TMS, right? So now here, the one that's being highlighted in yellow is actually the combinations of deference times and inverse times relay. So with the intentions to further reduce the operations times of the relay for the fault occurs here. So that's how we have the first, the second kinds of relay combined with third types of relay, forming us the fourth types of relay. Okay, so the use of inverse time overcurrent relay allow us to have selective trippings of the breakers for the radius feeders. All right, so now let's move on here. So there are three commonly inverse time relay being used for overcurrent protections. There are the inverse, very inverse, and extremely inverse. The difference among them is by looking at the slope of this relay in terms of time, current, operating curve. So the more inverse, which means that we have a more steep slope for the curve right now, or I should say a larger slope. So let's see, we have three characteristic curves right now, talking about the same pickup currents value. So if we are using a standard inverse, right? So standard inverse, you can see the slope is actually more steep. All right, so it will have a largest or delays of time. So what if I change to very inverse with intermediate slope? Intermediate slope which giving you an intermediate delays of time instead. What if I use extremely inverse right now? It will give you a shortest time delays, seeing as the slope is the highest. All right, so you can see different curve here is actually telling you difference in terms of speed to break the fault. All right, I'm talking about the same fault current value. So usually for standard inverse, right, will be used whenever there's a coordinations needed to be tripped together with the fields. Very inverse will be used for the power feeders, right, going through different directions. Extremely inverse usually we will use for those expecting to have large fault currents value, so we need a fast actions of relays. So generally, it will be applied for the distribution feeders or the power transfer and all. All right, so here are how we can have different kinds of inverse times relay, okay, based on the slope. But for this inverse times relay, it has problems as well. Let's see what is disadvantages. So as you has been observed through its characteristic curve, so for inverse times relay, in the event if I have high fault currents value, the tripping time is more, right? So with such kinds of properties, it actually makes it to very hard to decide what is the right relay setting so that we have selecting trippings of the breakers, especially for those generating system that is changing the generated power. However, with the fact that default time rate doesn't have these problems, seeing as its operations time is independent with the fault currents managed, so we'll make use of these properties here to solve these problems. So we'll combine the default times and the inverse times relay, giving us this, the IDMT relay, the fault kinds of relay. Okay, so IDMT relay, the full form is inverse definite minimum time slacks relay, whereby it have two characteristics, whereby this relay will work inversely for specific regions of current, and then it will have inverse relationship between the current and the times here, all right, for another regions of the current. So let's check out this characteristic curve here. So as you can see, this is time, this is current in x-axis. So whenever we have lower fault currents value, it will have inverse relationship. Whenever the current fault current is reaching higher value, it will operate with definite time characteristic instead. So which means that no matter how you increase the fault current values right now, the delays of times is always fixed at this constant value. But before this, you will have inverse relationship instead. Okay, so now let's check out these figures here. So we are having a comparisons in terms of characteristic curve for three different types of overcurrents relay. So this is time, this is current. So this one would be for a definite times relay. As you can see, based on your time setting, once the current reaches its peak occurrence value, it will start to trip. So here is the tripping regions for definite times relay. And here I have inverse times relay. All right, whenever the current increase, the operations time is reducing. And then the last one here, we have IDMT relay. So whenever we have small currents here, it has reverse relationship, which means that higher current, it will have lower in terms of time delay. But once it's reached to a high current region, it will have fixed response of times. So that these are the three operating curve for definite time, inverse times, and IDMTs relate. Okay, so now let's see the next slide here. All right, so we want to see how actually we can do the coordinations if let's say we're using more than one overcurrent relay. Some work as primary, some work as backup protections. So now let's check out, for example, for this case. All right, we have a radius systems again, generation source feeding the line divided into 1, 2, 3, 4 sections. We have bus bar A, B, C, D, E here. And each bus bar, or I should say, each substation here is feeding the maximum load current. A at 50 amp, B at 50 amp, C 100 amp, D at 50 amp. And each line sections here we implement with the overcurrent relay R1, R2, R3, R4. So we know that whenever we want to do the coordinations, right, we will always need to refer the relay that furthest away from the generation source. Let's say I'm using the inverse times relay, okay? So now we will need to consider what is the fault that could occur near this bus bar A here, or between line sections A and B, that consider as the internal fault for this relay 1. So for instance, if this fault occurs at the ends of the line is at 500 ampere, okay, we need to consider this to look for what is the TMS value for this relays right now. So check out the figures at the top. Operations times of a relay, This is, let's say, is in terms of fault current in the units of ampere. All right, so in the event for in between line sections A and B here, we know that the fault current occurs is 500. So we draw a vertical line here at 500 ampere for the first case between A, B. All right, so I want to select the right TMS values for this overcurrent relay. So you'll notice that whenever I have fault occurs here 500 ampere, it will operate at point A. If I select the TMS at 0.025 seconds. So which means that in the event 500 amp fault occurs within line A and B, so it will take the time close at 0.15 seconds to trip this fault. Are you okay? That's how I select the TMS value for relay 1. And then, right, I know this relay 2 should work as a backup for relay 1 to trip this fault, right? So which means that there will be delays of times for this relay 2. So let's say I keep the time margin at 0.3 seconds. So which means that if the same fault occurs at A and B, all right, time is in y-axis, right? So you wait for 0.3 seconds for this relay to wait for 0.3 seconds, which is at point B here, to select the TMS value for relay 2. So you can see it is actually much more higher as comparing to 0.025, right? So the suitable one will, let's say, at this value, 0.07. So now I have select this relay 2 here to work as this TMS value 0.07 second, whereby in the event if there's a fault occurs between A and B at 500 ampere, it will work at this time, which is 0.5 seconds to trip this fault. So you can see it has wait for 0.3 seconds from 0.15 seconds for this first relay. So that's how I choose the TMS value for relay 2. But I could have internal fault for relay 2 as well, right? So which it should work as the primary protections. So we'll come across the second case right now. Okay, so which means that in the event if I have fault occurs between B and C, where the expected fault current value is 1200, I will need to consider this, all right, to have this relay 2 here work as the primary protections. All right, so just now I have created this relay 2 here according to relay 1 as a backup, right? And I have chosen the TMS value for relay 2 at 0.07 seconds, right? So in the event if I fault occurs between B and C here at 1200, so I will need to draw another vertical line here. All right. So for this relay 2, right, it will operate at this point, whereby whenever I have 1200 of fault currents appear between B and C, it will take the times, all right, close at 0.24 seconds to trip this fault as a primary protection. Are you okay? All right, but for this relay 2 in the event it's not working, I know I have backup from relay 3, right? And I will keep the same margin at 0.3 seconds. So within the same fault, I wait for 0.3 seconds to choose the TMS value for relay 3, right? Which is at this value here, 0.086, in which this relay 3 will help to trip this fault if relay 2 is not working at this time, all right, which is at point D here, close at 0.54 seconds. That's how I choose the TMS value for R3, in which it need to grade according to relay 2 here as a backup. And then I also know that for this relay 3, it should work as the primary protection for those fault occurs between C and D, correct? So I will come across the third case right now. So I need to know what is the expected fault that occurs between C and D. So now I know it's 2000. All right, so I will need to draw a vertical line right now at 2000. So just now I have selected the TMS curve at 0.086 for R3, right? And which means that if you draw a vertical line here, so this relay 3 will work as a primary protection to trip this fault here, 2000 at this point E. So at the time close at 0.34 seconds as the primary protections. And then again, I have R4. That's as the backup for R3. I will need to keep the same time margin. So which means at this point here, I will need to add 0.3 seconds to find what is the right TMS value for R4. Okay, so go to the next slide. Same fault current, right? To select the TMS curve for R4, which is higher at 0.097. So this indicates that R4 will as the backup for R3 to trip the fault at this moment, right? Which is at 0.64 seconds. Okay, and this R4, it should have internal fault occurs as well, right? Which is between lines D and E here. So we will have the fault case, all right, which is the fault that occurs between these two, these two substations. So let's say the expected fault at the beginnings of the line is 3,500. So just now we have already selected the TMS value for R4 based on R3, right? Which is at 0.097. So with the expected fault at 3,500, we know that the relay fault will work as a primary protection to trip this fault at this specific time at 0.38 seconds. So that's how we do the time coordination. But right now, for this relay fault, there's no backup, okay, because it's near the generation source. So it will only rely on this R4 here to pick up this fault. Okay, this is how we can choose the right TMS value. In terms of time coordinations, whenever we are having multiple overcurrents relay to be used in a radial system for overcurrents protections. Okay, so now let's move on here to the next slide. So after you see the demonstrations of the coordination for your 4 overcurrents relay right now, so you see that there's actually rules for us to do the settings for the overcurrents relay in terms of pickup currents value as well as time adjustments value. So I will start to talk about the plug settings value first. So whenever we are using more than one relay to be used to protect a specific power networks, the relay coverage areas, right, it should reach at least up to the end of the next protection zone. So if you check out the figures here, remember this one? Generation source, transformer, the line, all right, we have R1, R2, R3. We can use different kinds of overcurrents relay. If I talk about different times relay, you can see its coverage area not only within the zone, it will reach to next zone sections as well. So you can see if we are focusing on R1, this is the coverage area up to the next zones here so that it can work as the backup protections. So how about, so inverse times relay is like this, right? And this is the IDMT's relay. So how about for relay 2 here? Same. From BC up to D here. So we have R2 as a backup for relay 3. So with such kinds of setting for the reaching area for the relay, it can have the backup protections. Okay, the plug setting must not less than the maximum normal loop currents value so that it able to allow the normal current flowing through continuously, right? So we know that it should not trip under normal conditions. All right, so it will be higher than the normal currents value. And this relay pickup value, it will be approximate 1.05 to 1.3 times of the plug setting being chosen. This is following the standard plug. So with such a case, if we go to the next slide here, there are things need to be considered if we want to tune the plug setting for the overcurrent relays, right? So let's refer this diagram here for explanations. So what would be the possible issue faced if we tune the plug settings value? This is actually the radio distributions networks where the transmission line has been divided into 3 sections right now, where substations A, B, C, D. Okay, suppose it state that the rated full load current value for this radius feeder is 200 amp. This is normal current value at 200 ampere. So ideally, we will think that all of these relay, let's say relay 1, 2, and 3 here, will set the plug setting exactly at 100%. So which means that it will pick up the fault at its exact magnitude. Okay? But with such kinds of setting, right, plug setting at 100%, it will actually have some problem whereby we will lose in terms of selectivity. In the event, if let's say we have overload situations, the healthy sections might have unnecessary tripping. So let's see the next slide here to further understand this statement. Okay, so what happens if we have overload situation between line C and D here? Up to 20%. 20% of 200, which means that we have fault current flowing through right now between C and D is at 240 ampere. Okay, now, if we follow the standards, we know the relay might pick up at 1.05 to 1.3 times. So what happens if I set the plug setting at 100% for each of the relays right now? So if we consider this relay tree following this relay tree might pick up at 1.3 times of its plug settings. 1.3 of 200, which is 260 lah, right? What happens if we have relay 2 here, which works as the backup for relay 3 and is picked up at 1.05 times at its plug setting. 1.05 of 200, which means that the pickup current for this relay 2 is 210. So under these situations, overload between C and D, 240. If we have relay 3 pick up at 1.3 times at the plug setting, which indicates this 240 amp is lesser as compared to its pickup current value. But how about for relay 2 here? So 1.05 of plug setting, which is 210, obviously it's able to pick up this faults right now for this relay 2. So under these situations, we know that relay 2 will pick up this fault, but relay 3 doesn't. So if we want to have a good selectivity, relay 3 should trip this fault instead. All right, so right now with these situations, these sections B and C, yes, it still can be disconnected. Once this relay 2, the expired of the time delay has been finished, which means that if let's say we know that this is put as a backup, if the time delay has been expired, then it will help to pick up this fault. Okay, so this is basically the problems we have is we have plug setting at 100% for all of the relays right now. Okay, so we have poor in terms of selectivity. This one should work to trip the faults as a primary protection. We should not rely on the relay 2 here. So what we can do, we need to modify this, the plug settings here. Should not set at 100%. You should set based on these formulas here, which is the standard plugging margins, whereby the pickup current value that would as the backup should be more or equal than this ratio 1 over 1.05 multiplied with the pickup current value for the relay that should work as the primary protections, which means that the plug setting here should change according to the pickup current value from the relay tree. All right, so now let's see how we can do the modification so that we can solve the previous problems. So we know that plug setting for relay 2, this one should be changed. So we'll apply these formulas in loops. So it has to be set in this way, more or equal than this 1.3 over 1.05 multiplied with this plug settings of relay 3. So let's say here is 100%, it doesn't change this for relay 3. 100% of 200 amp or 200 amps here. So always you refer to the primary set. So 100% of 200 amps here, we know here is 200, right? 200 multiplied with the ratios here. So the pickup current value for relay 2 should be set more or equal than this value, 247.62 ampere. But we are interested to know what is the percentage values, right? So how actually I can convert it into percentage value? So if you go back here, you know that the rated current is 200. So you have 247.62 divided with 200. then multiply with 100%, so you can get this value. So the plug setting have to be choose much more higher, more than 123.8%. But this is not the average standard value we can choose for the relay. So usually the average plug setting for relay will be in this range from 50% up to 200% here in the step of 25%. So I will choose the closest one, right, which is 125% for this relay 2 as the plug setting. So if you change this instead of 100, right, so you change it to 125, so you will notice that the pickup current value for relay 2 will be 125% of 200, right, which is at this value here, 250 amp. That's how we maintain the selectivity of this protection system. Okay, similarly, right, for relay 1 here, the plug setting should change as well. It should not keep at 100%. We need to modify it to this value, 175%. How actually we can get these percentage values here? Same, apply this formula, okay? So the plug setting for the relay 1 has to set following these formulas here, 1.3 over 1.05 multiply with plug settings of relay 2. All right, just now we have set 125%. 125% of 200, which is your pickup current value for relay 2 here, multiply with this ratio. So we know for relay 1, the pickup current value should be higher than this magnitude, 309.5 ampere. Convert into percentage value. How? We know that the rated currents between A and B here is 200. So 309.5 divided with 200 multiplied with 100%. So I will need to set the plug setting here more than 154.76%. Again, this is not the standard value I can get from the relay. So I need to standardize the value I can get. The closest value I can achieve is 175%. All right, so that's how I can get the values here. Okay, so that's how we adjust the plug setting for the overcurrent relay here to solve the loss in terms of selectivity during the time if we have overload conditions for the radio system networks here. Okay, so this is the first way whereby these formulas is actually applied in the event if there's no transformer in between. So what happens if I have transformers in between instead? So this time you need to use the power ratings of the transfer to find what is the pickup current value. So in this slide, it shows you the summary whereby how we find the plug settings. One way is by using the standard plugging margin, in which this is what we have seen in the previous example. The other way is by using the power ratings of the transformer. And this is only used if there is transformer involved within the power network. All right, so you can see it's a power divided by square of 3 multiplied with the wattage in terms of kilowatts. All right, so now you might ask, when would be the situation I should apply this formula or I should use the standard plugging margin? So let's check out this image here. So we have a generators, okay? After the generators, we are implements overcurrent relay, R1. So after this relay 1, we have a transformer, okay? Then we have another relay. So this is actually the circuit breakers lah. Okay, so after this relay, we have the bus bar. Of course, we have multiple feeders. It has its own protection system as well. So in the event, if I want to find the plug setting for relay 1, right? So, and this relay 1 is located at the primary side of the transformer. For this situation, the current flow doesn't change by the transformer ratios here. So I can directly use the standard plugging formula, this formula, to find the plug setting. Okay, what if for relay 2, which is placed at the secondary side of this transformer? So the current flow here and here is not the same. It will change based on the transpose ratios from these transpose, right? So under these situations, to find the plug setting for relay 2, you will need to use the power rating equation instead to find what is the pickup current value for this relay 2. So again, primary side, use this one. Secondary side, use this one. Whenever we have transfer in between, we must use this formula for the relay that locate at its secondary side. So we have a questions in the tutorial relating to these kinds of connections. I think you can actually try it out. Okay, so now let's move through the light side here for this relay in terms of tuning for the time setting. Okay, so do you still remember for us to tune the operations times of the relay, we are actually using the time multiplier settings. This is for the inverse times relays, right? And has been chosen in a way for the relay that is occurs or placed at the furthest away from the generation source. It will have fastest operations time. So remember this one. We have relay 3, 2, and 1. The relay 3 here will operate the fastest, and whenever we're getting closer to the generation source, this relay 1 will have lower operations time. This is the rules of times of setting the time. Remember, always the one further from the generation source, its pickup times will be fastest as comparing to the one closer to the generation source. So there might be times, right, where the questions might ask you to find what is the actual operations times of these IDMT's relays based on the plug setting multiplier as well as TMS value being chosen. So you can apply these formulas here. So we have 3 over log PSM multiplied with TMS value. Do you still remember what is plug setting multiplier? So basically, it can be found by using the fault currents. You want to pick up currents, remember? So you will see what will be the positions of the tapped for this fault current for this overcurrent relay. And this is based on the value chosen. And these formulas, right, is only applicable if plug setting multiplier is less than 20. So for example, 80, you put 18 here. But what happens if I have PSM value here more than 20? So under these situations, it's actually the same formula. You just keep these PSM values here always at 20 to find what is the actual operation times of these relays. All right, so for example, 21, you put 20, 30, also put 20 to get its operations time. Okay, so I think that's it. So with this slide, it's bring the end for this chapters number 4 here. All right. So we have seen the components dealing with overcurrent situations, the fields. We know fields can't use for backup protections. That's why we have overcurrent relay. And overcurrent relay have to be always used together with the circuit breakers, right? So that it can trip the fault conditions automatically. And for this overcurrent relay itself, based on what kinds we have here, so we can actually tune the pickup current setting that is for definite current relay. Other than this, like definite times relay, inverse times relay, and IDMT's relay, here we could have 2 settings, inclusive of operations time as well, by playing around with the time multiplier setting. The higher the value would be, which means that the longer the delays of time for the operations of this overcurrent relay. And we have also gone through the characteristics of these 4 different kinds of relay, which one is suitable for different conditions. All right. So basically that's it for chapters 4 here. So do you have any questions? Hello, anybody home? Hello, hello. No question. No question now. You're so fantastic, this group. Okay. So, all right. So for this case, for these chapters, right, that is the questions, I mean, for the tutorial. I hope you can try it out. It's very important. And these Wednesdays, right, we have tutorial class and I will discuss the tutorial question which is relating to previous chapter in, if not mistaken, it will be on instrumental transformer. So that's it for today. If you have no questions, thanks for your time, and I see you on this Wednesday